Hello, and welcome to 607-181 Hydrology and Conservation, a prep video, this one dealing with hydrographs. We've talked about rain falling from the sky. So, we've talked about here's the ground, and we've looked at the rain falling from the sky from our low clouds. And we've done the rainfall for different year storm events for various year storms, which gave us inches. And then we were able to translate that into intensities, which is inches per hour. So we understand for different year storms, we can have different intensities of this rain coming down, hitting the ground. So we've looked at the rainfall itself up here. Now today what we're going to concentrate is what happens down here. Because all that rain is going to accumulate to what we call a point of analysis. And we're going to look at how that water accumulates to that point of analysis and how to calculate that value. So we've looked at the rain coming down, so the rainfall coming down, and now we're going to look at how the water is actually accumulated and develops into how much flow goes by our point of analysis. So let's just say we have an area right here. And we're going to call this point right here, this is our culvert pipe or whatever going under a road. And this is our point of analysis, right at the entry point to that culvert. And we want to look at what is the flow of water through this pipe. How's the water flowing through this pipe? The first thing you notice, we have our drainage area. This is the area that drains to this point. So if a drop falls on this spot right here, it's going to somehow get down to that point of analysis. Conversely, if a drop falls out here, it goes someplace else. Or a drop out here, it goes someplace else. So this is our drainage area for this point of analysis, meaning this line right here is the divide line. So this is like the continental divide for this drainage area. Anything inside this line flows to our POA, and anything outside this area flows away from our POA someplace else. So the only thing that this drainage area is calculated or measured based off of all the points, all the areas where if a drop of water hits there, it flows to our point of analysis. Anything outside this flows away or someplace else that we don't have to worry about that. So this is our drainage area. I have a lot of these marks on here. So the key part right now, we know our drainage area, which is A. And now the other key part that we need to know is a time of concentration. Time of concentration. And what a time of concentration is, we assume that the cloud comes over our drainage area and drops water. So we're going to assume that here's our rainfall, right? And so we've dropped our water right here. Still want this to be our POA. So the time of concentration, it's a time if one droplet falls every grid point on our drainage area. The time of concentration is the time it takes for the last initial droplet to make it to the POA. So our time of concentration is going to measure, typically it's the point where you're furthest away, but it might not be, but typically it is. So it's going to take, how long is it going to take this drop of water to make it down to our POA? And that's going to be our time of concentration. The time it takes for that last droplet, the droplet furthest away, to reach our point of analysis. When the first droplets hit, bam, the first wave of drops hit, the time it takes for that last droplet to finally reach the finish line, that's our time of concentration. And why is that? If we look at this, we have our droplets hit. So let's do a count. And so let's say our time of concentration is going to be, our droplets going to go here. So let's take 1, 2, 3, 4, and 5. That's our path. That's going to be our path that that water droplet takes to reach. And then 6. So we got 6 steps right now. We got 6 steps in this process. So we got time of 0, time of 1, time of 2, time of 3, time of 4, time of 5, and time of 6. So we're going to see how long it takes for the water droplets to cross, and we're going to count the number of droplets that cross our POA right here. So we start off with our droplets. So our droplets fall from the first drop. They hit the ground. Has anything crossed our POA with the first droplet line? We still have 0 right here. Now all the droplets go across. So we go 1 time interval over. 1 time interval over. So this drop will reach the POA, right? This drop will come here. This drop will come here. This drop will go, oops. This drop goes over to here. This droplet comes down. This droplet comes down. This droplet comes over. This droplet comes over. Let's just say these come down to right here. This, oops, order. So this droplet will come down here. This droplet will go across to here. This droplet will come over to here. This droplet will come over here. This droplet will come over to here. This droplet will come over here. This droplet will come over here. And this droplet will finally come down to here. So our droplets have moved down towards our drainage area. So at time 1, we have 1 droplet that's made it across. Now, the rain keeps on going. So the next wave of droplets come in. And we'll color code these different properties. Let's just, for sake of keeping this straight, we'll give it an orange color. So the next group of droplets now hits, and let's count how many droplets come across. Well, right here, this one now has gone downstream, so it no longer is in our POA. And so now this will slide here, this will slide here, this will slide here, and we have effectively 3 droplets of water. At time period 2, we have 3 droplets of water at our POA. These will come down to here. These effectively go over to here. These droplets of water come over to here. These droplets drop down. These droplets will come down to here. These droplets come over to here. These droplets move over there. These come down to here. This one comes across, and this one down. So at point 3, we have, at time step 2, we have 3 droplets of water. Now we add another rain. So give this property, let's say it's green. And so we have 1 droplet from that initial one. Now we have these guys go down. So we had send it back. So these guys all so those all are passed. And now we got these droplets come in. So these droplets hit our POA, right? So we'll put these right here at our POA, along with, whoops, we got ungroup these, grouping, ungroup, so these will move. So that one comes down too. And so at the next time step, it's step 3, we have 1 green, we have 1, 2 from the orange wave of water, and we have 1, 2, 3 blue ones. So we have 6 droplets of water at step 3. We have 6 droplets of water right now that are in our pipe. So we have 6 droplets of water in our pipe. Right there. And the rest of these move forward. So these come over, these come over, these come over here. These come down. This comes over here. These come over here. These come over here. These come down to there. This one comes over here. This one comes over to here. And we get our next drop of water. So our rain keeps on dropping water until we reach our last blue dot coming across. So I'm going to turn these purple. And I'll explode these. So these go on downstream. And let's see how many now we get at time step 4. At time step 4, all these have come across. These have moved out of the way, so they're just off the screen. We'll just delete them. Now let's see how many we got. We got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So now we got 11 here, right? We have 11 drops of water in our point of analysis from our stream. So we've gone from 0 to 1 to 3 to 6 to 11 now, crossing over. 1 from the 4th iteration, 2 from here, 3 from here, and 5 from here. So those go, and all these move forward. So all these would move down. These will move over. These are moving over. These move down. These move down. These move over. These come down. This one moves over. And this one moves over. And we still haven't flushed away all of our blue dots yet, right? We still haven't got our blue dots out. So now we got to do another step. So we drop another thing of water. So our rainstorm keeps on going. And we'll make these, let's make these, how about this color? That works. So now we got to check how many, now we do our next time step. These will come across our POA. So how many do we have here? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we're up to 16 drops of water now, right? 16 drops of water that's crossed our pipe. So now we got moving forward. So those come down here. These come across to here. These come down to here. These come over to here. These come down to here. These come over to here. These come down to here. And this one comes down to here. Now we still have some of our original droplets that haven't made it across yet. So we got to keep on raining. These yellow. I can't see those. How about peach? That works. So we've dropped our rain, and now we do the next step. So let's see how many come across. So in here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So we have 19. So we have 19 droplets of water. Whoops, one more. Sorry, I missed one. Because we got to ungroup this one. So this one would come across too, which will make us 20. So that makes it 20. droplets of water that made it across. And if we notice, this is the last group that contains our initial droplets of water. So our initial droplets of water are in this last group. We have no more droplets of water after this group from the initial wave of water that fell to the earth. So after this point now, we can stop raining. So since we stopped raining, now we've reached our time of concentration. Our time of concentration in this case was 6 steps or 6 iterations. Could be 6 minutes, 20, whatever, 6 units of time. And now we do the next step. We keep on bringing these points across. Let's go down. Now, just because we've now reached our T sub C, right? Let's group this. Just because we've reached our T sub C here for our time of concentration, does the rain stop? Does the water stop at our point of analysis? The answer is no. We keep on going, right? So what's the next step? 7. How many will cross now? So now we got to check these. All right, so didn't count. Oh, well. Do it the hard way. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So now we have 19 coming across at time 7. Delete those. So now we do the next step. Notice we haven't added any more because we've reached the time of concentration. So we're no longer going to be adding water to the situation. So now we go time 8. At time step 8, what do we do? So these will come across now. And how many do we got? We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. So we have 17 there. Next step. We go through, Now, step 9. Let's see how many comes across at step 9. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 came across here. And we come across here. These are down. So come over. Now step 10. What do we get? So we get 1, 2, 3, 4, 5, 6, 7, 8, 9. Step 11. These guys come down, and then these guys get counted, which is 1, 2, 3, 4. So step 11, we're at 4. Group. And then at step 12, we're back at 0. So this right here is the hydrograph, or the drainage characteristics of our little plot. This is how water droplets drain through this point of analysis. In order to calculate our point of analysis, if I'm sizing this pipe right here, this pipe, I have to figure out this one right here, my maximum amount. My max, which we call Q, is what we have to size the pipe for, Q max. So this is what we'd size the pipe on, that we'd have to accommodate 20 droplets coming through that pipe. That's how we'd size the pipe. But the pipe itself has this characteristic. Even though the rain stopped, this is where the rain stops, notice there's still droplets coming through our pipe. And this is the hydrograph. And we call this a unit hydrograph because we just did one drop, right? So this would be a unit hydrograph because we had one drop. Now we have, instead of doing one drop, we could declare this to be 1 right here. So it'd be 1 unit of Q max would be relative to all this, and this would be proportional. But this is the drainage characteristic going through our pipe right at that spot. Thus, this is the hydrograph. And this is why when it rains, right, you see the lake swell up and everything, but the drainage area keeps on coming in until that time period at which, even though the rain stopped, you still have a lot of stuff coming through. And so if you have 2 or 3 tributaries coming through, the rain has stopped, but that lake, the river still could rise during that time period. That's why it doesn't rise right away. There's a delay in the process. And this showcases with these hydrographs the delay. Now, each location, each point of analysis is going to be unique for that point of analysis. Each drainage area is going to be unique in terms of how they set stuff up. Now, we could do one of two things. One, we could go out and actually physically measure each drainage spot to figure out what the exact hydrograph actually looks like, which would be very costly and spend a lot of times, or we can approximate. And here is the hydrograph. I'm going to group this. copy it. And there's been a number of attempts to do something with this hydrograph. And so I'm going to just properties, I'm going to create this out. So the key spot right here is your T sub C. So regardless of what your drainage area does, we're going to set this as a T sub C. And we're going to try to come up with a unitless hydrograph. And the first one we're going to look at is the rational, the base rational hydrograph. So we start with the TC, and we know this is our Q max, right? Our maximum Q. We'll talk about how we calculate this coming up. But let's just say for our hydrograph purposes, this is our Q max. The rational hydrograph said, okay, then if that's our Q max, we're going to start out here, go to here, and then go back down to 0. So we're going to start out and then come back down in a straight line. So if this was 20, right, for Q max, then our model, this is our model. Our model is going to say, what is that? 20 divided by 6. So this would be 3.3 6.7 10 13.3 3 16.67 and 20. And then back down, conversely, 16.67, 13.33, 10, 6.67, 3.3. And what did you notice on this? We were stronger. We overestimated based on our methodology. We overestimated what was actually there. So this is a conservative estimate. But on the back side of this hydrograph, what happened? Look, 19 to 16, 13, 10. We've underestimated. We've underestimated how much water. We overestimated here, which was conservative, but we've underestimated the effect back here. In addition, we haven't really estimated, we've had this situation where a lot more came across because it slowed down, depending on the topography and everything. So the back end, under the base rational method model, underestimated the back side of our hydrograph. So our model gave us a lower value than what we were seeing in terms of a prediction. So that was the base rational method. So what we've came up with is what's called the modified rational hydrograph. And we still have the same Q max, 20, right? The same T sub C right here. The same drainage up here. All this stayed the same, right? So this is the same. But where we changed was on the back end. Instead of being at 12, because this distance was TC on the previous one, this distance was time of concentration, and then this distance was time of concentration. they were the same, 6 units of time to 6 units of time, to get us 12 units of time. The modified said, we're going to extend this out to 1.67 time of concentration, or 1.67 times 6, which would be, in our case, 1.67 times 6, which is equal to 10. So we're going from clear out here to 16. So we're going to extend our time of our model. Remember, this is the model. This isn't actually what's happening. We're going to extend this out from 12 to 16, which gives us 1.7 times our time of concentration, or a total hydraulic event of 2.67 times our time of concentration. And now our new model goes from here down to 16 over here. So what does that effectively do for our time? This becomes 18, 16, 14, 12, 10, 8, 6, 4, 2, down to 0. Now look at that. Now it's a much more conservative model. A more conservative model. Because if you're going to use a generic model to estimate your drainage for that pipe, you want to do a conservative model, means that you want your model to estimate more water than what's actually out there, so you accommodate for all the water that's going to be out there. So you want your model to be more conservative than your actual. And in this case, except for these 2 points right here, everything else is a much more conservative model. So we're over conservatively estimating more water here, and right here we TN, and we're right here. The only place we're less conservative is through here. And so that's a good trade-off. And so the modified rational hydrograph is what we typically use when we start dealing with a hydrograph. And this is the reason why. If you look, the standard hydrograph, it underestimated the back end of how much water we had. Where this one overestimates, or gives us a more conservative model. So therefore, the unitless hydrograph that we typically use when we have no other information for small flows is this. This is Q max. This is T sub C. This is 1.67 times T sub C for a total from here to here of 2.67 T sub C. And so this is the modified rational hydrograph. Which is modeling our drainage areas. So this is modeling the flow that's going to be coming across this point of analysis, this being our actual hydrograph. And as we saw right here, this is the modified hydrograph model that we're going to use in place of, in the absence of an actual hydrograph. Because the modified rational gives us a more conservative result than the actual hydrograph, typically. And so with the modified rational, whereas the rational didn't give us that whole thing. It balanced it nicely, but didn't really give us an overestimated model. The rational modified model gives us a more conservative model that covers both the front end and back end. And this is the thing. So all we have to do is calculate Qmax, our T sub C, our time of concentration. So as long as we know Qmax and T sub C, we can estimate the hydrograph for any given point, as long as it's a small drainage area. So this concludes an introduction to 607-181, a prep video for hydrographs. Thank you.